Hello lovelies, and welcome to the second video in the series on integration. Here are a lot more examples at a slightly harder level for you. If you check the descriptions, there'll be links to all of the other videos, or you can find them all in this playlist. Now, there are lots of examples here, slowly getting harder. What you can do is look at the question, pause the video, try it, and then play it to see if you get the answer right. If you want to see if you can use this skill in an exam situation, then over my website there are lots of predicted and practice papers for you to download straight away.
We're going to have a look at some special cases in integration, and first we're going to have a look at trigonometry. Now with trigonometry, let's say we've got a function of x, and let's say that's equal to sine of x. So if you were to differentiate this, and you get f dash x, when you differentiate sine, you get cos. And so if going one way is differentiation, then going the opposite direction is integration. Now we're starting off with an integral. It's the integral of 8 sine x. So they've got the integral symbol and the dx are just telling you what to do. We're going to integrate. And so we're going to go from sine to something else. So we can see with what we've just written out, going from cos will get you back to sine. Well, we're starting out with sine, so we need a few more definitions. So the next one is going to be, if you have a function of x, and you have cos of x, then when you differentiate that to get f dash x, when you differentiate cos, you get a negative version of sine x. So again, we can think about this going in two different directions. So if you differentiate, you go from cos to sine. And if you integrate, you go from sine to cos. And this is the one to be relevant to this question, because we're starting it with sine and we want to go to cos. We should go through one more though. If you have tan of x and you differentiate that, then what you get is you get sec squared x. So again, you differentiate, you go from tan to sec, and if you integrate, you go from sec to tan. So with that in mind, again, we know we start with sine, so that's going to end up getting us to cos when we integrate. Now, there are a few things with this. So the first thing is that if you go from a negative sine, you get a positive cos. So we're going from a positive sine, we'll be going to a negative cos. The other thing to think about is the 8, and for this question, that 8 is going to stay the same, but we'll have more to say about that on the next question. The last thing is, like all integration, there might be more to it than this, and there might have been a whole number in here that got lost along the way, so we've got to write the plus c. That's because negative 8 cos plus 2 would differentiate to 8 sine x, and negative 8 cos x plus 100 would also differentiate to 8 sine x. So we just have to keep in mind there might be something else to this. So now moving on to the next question, we can see we're starting with our integral with a cos. So we have a look at our little list here. We're going to look at starting at cos and moving through integration to something else. So we look at the one at the top, start at f dash x, and we integrate, we go from cos to sine. So that's the first thing we can write down. The cos is going to turn to sine, and the angle's not going to change either. The angle's going to stay the same. Now, the next thing to consider is positive and negative numbers. We'll start with a negative cos. Now you'll see a positive cos becomes a positive sine. So a negative cos is going to become a negative sine. The other thing to think about is the coefficient, the 6. Remember, when you integrate, when you do it with powers, you divide by the new power. And with this, it's going to be similar. We're going to be dividing by the thing on the x, the kind of the coefficient on the angle instead. So we're actually going to be doing 6 divided by 6 here. And 6 divided by 6 is 1. So that means that our final answer is going to be negative sine of 6x. Now, this is assuming you're familiar with the differentiation video, because if you're not sure about differentiation, you might be a little bit confused at this point. So let's say we had f of x is equal to negative sine of 6x. When we differentiate this to get f dash x, So we kind of follow the opposite of what we've just done. Sine becomes cos. And then what happens is the coefficient on the angle, so the 6, that comes to the outside. And so this is how we get back to our answer. So you can try differentiating once you've got your answer to see if you get back to the original question. And if you do, then you know your integration has worked. But again, if you're not confident with differentiation, then you need to get confident with that first before you start watching this video in full. At the end, remember, because I almost forgot, very easy to forget, put the plus C on the end as well. So moving on to our next question, we can see we've got the integration notation, and we're integrating 8 sec squared 8x. So have a think about how we integrate this. We can see that sec squared is only there once, and it's when you integrate sec squared, you get tan. So I know that I need to integrate this. Sec squared 8x is going to become tan of 8x. Then we have to think about the coefficient on the sec squared. It's an 8. I'm going to divide it by the number in the brackets. So we're going to get 8 over 8 tan of 8x. And again, divide a number by itself, you get 1. So the answer is going to be the tan of 8x. Then we can add the plus c. Now, as well as trigonometry, we can look at other things. So, for example, we can look at logs. So if we've got a function that's equal to ln x, then when we differentiate that, you should remember that ln x becomes 1 over x. So going in that direction, you're differentiating. Going the opposite direction, you're integrating. Now, we don't have 1 over x here. We've got 5 over x. So how do we deal with extra numbers involved? So another thing to think about, say f of x is equal to, let's say, ln x cubed. So you've got a power on the x. Then we differentiate. That's going to give you 3 over x. So it's actually the power on this that's going to end up being the numerator. Again, going in one direction, differentiating. In the opposite direction, you're integrating. So now we can bring this back to our question. So we know we're integrating, got the integration notation. We've got 5 over x. So if 3 over x becomes ln x cubed, then 5 over x is going to become ln x to the power of 5. And as usual, we include the plus c. Next, we've got e. So remember, e is quite special when you differentiate it. It's a rational number like pi. It's kind of 2 and a bit rather than pi being 3 and a bit. And when you differentiate e, it actually stays the same. So e to the power of x, if you differentiate it, you also get e to the power of x. Now, there is a twist with this, which is when you have e to the power of, let's say, 2x, when you differentiate it, again, e stays the same, so you still have e to the power of 2x, then the 2 comes down to the outside as well and multiplies by the coefficient. In this case, it's 1, so 2 times 1 is 2. So we just got e in its own. Differentiating and integrating is the same. But when it's not on its own, then it's going to be that differentiating, integrating, there's something else to look at. And that's the case with this question. So again, we've got the integration notation. We've got 5 lots of e to the 5x. So the first thing we can think of is that when we integrate e, it's not going to change. We're still going to have e to the 5x. That's no different. The change comes when we do have kind of numbers on the x. We have coefficients. So we have a coefficient on the e, which is the 5, and we divide it by the coefficient on the x, which is 5. And so we have 5 over 5e to the 5x. 5 divided by 5 is 1. So we're just left with e to the 5x as our answer. And of course, plus c. Now, all these kind of more interesting functions can also be represented on a graph. So, for example, you've got the 1 over x graph for our question here. We've got an x and a y-axis. It's going to look something like this, and we'll go with the negative as well, actually. So it might look something like this. And so we've got the integration notation, but you'll notice we also have the numbers. And it works the same way as having those numbers with regular integration. So we've got a 5 and a 4. So what we're saying is, on this graph 1 over x, we want to find the area between 4 and 5 under the curve. So that's what we're going to try and do. So the first thing to do is just integrate. So we can see that 1 over x integrates to give us ln x. And of course, it's going to be plus c as well. But now we can substitute the numbers in. So substituting the largest number first, the 5. And that's going to give us ln of 5. Then we've got the plus c. And we can close our first bracket. Then we're going to take away from that the second substitution, which is the 4. So we're going to have ln of 4 plus c. And we can close those brackets. And this is something we can put into a calculator to work out. So press the ln button, press 5, and you should get an answer. So I'm getting 1.609. Now, what am I going to do the answer to? If the answer to 2 decimal places, let's write this to 3 decimal places. Then we've got the plus c, and then we're taking away ln of 4. Again, let's write this to 5 decimal places. And then we're taking away the plus c, so we're taking away c. Now, you might remember from when we did this with regular integration, the c's are going to cancel out. But then we need to do the takeaways with the ln's. Now, we use these 5 decimal place figures. So 0.60944. Take away 1.38629. We're going to get what should be our final answer, which is 0.22 to 2 decimal places. Let's do 3 actually. So 223. If you want a high level of accuracy, you can just look at what's happening. We've got the ln5 number. So you can type ln5 into your calculator. Perhaps put brackets around the 5. Then take away from that ln4. And that should give you the same answer without any of the rounding. So just be a little bit careful with rounding errors with numbers like this. But you can see here that it's pretty easy to type them both into the calculator to take away next to each other anyway. So going back to what this means, it means the area under the curve, 1 over x, between 4 and 5 on the x-axis, the area is 0.223. It's a very small area, actually. Now, the next question, similar kind of thing. So we have an integration notation. We have numbers to substitute. So we're going to find the area under a curve. The curve is 2 over x. And this should be pretty simple to integrate. So 2 over x is going to be ln x squared. Again, just looking at a little key here and seeing that 3 over x becomes ln x to the power of 3. And yeah, it's plus c, but we don't need to worry too much about plus c because we know it's going to cancel out in the next step. So that next step is to substitute. Substitute the largest number first, 3. So we've got ln, then we've got 3 squared. Now you could write a plus 3 here. We know it's going to cancel out, so we might as well just leave it. We'll substitute in the 1. Now ln of 1 squared. Again, we can start to work this out. So we can do 3 squared is 9, so we want ln 9. Now again, we could get a value for this on our calculator, and I will write it down. So it's 2.19722 to 5 decimal places. But actually, it might just be easier to write down ln 9. Because then for the next step, we're going to take away ln of 1 squared, which will be 1 squared is 1, so ln 1. And that actually gives us 0. We've got ln 9, take away the ln 1. And you can just type that into your calculator, and it should give you the same answer, but without doing any rounding until the very end, if you do it that way. So ln 9, take away ln 1, and you should get 2 to 3 decimal places, actually, 2.197. So again, with questions like this, you can work everything out and write it down to a number of decimal places, but you might as well just think about writing the entire thing into a calculator all at once at the end. And of course, this question is a little bit easier because we're taking away 0, so we didn't really need to do the ln1 because we knew to get the same answer. The last step's going to be up at the top. The integral of 2 over x between 1 and 3 is equal to ln x squared plus c, which is equal to 2.197. Now, for the next question, again, we've got our usual notation. The thing we're integrating is a little bit more complicated, but if you remember, if your function of x is equal to, let's say, 3 to the power of x, then when you differentiate it, what you get is you get still the 3 to the power of x, and then you also get ln of 3 as well. And those two things are multiplied together. So that's when you differentiate. So if you integrate, that's going back in the opposite direction. And so we can kind of see the pattern here. we've got 2x ln2. So we integrate that, that should be 2 to the power of x plus c. So now we can substitute into this. Largest number first, the 5. And so we're going to have 2 to the power of 5. We can leave off the plus c because we know that's going to cancel out. So we're going to substitute in the 4, and that's going to be the 2 to the power of 4. Now, you could work this out step by step, but again, we can see we've only got one thing in each bracket, so we can do 2 to the power of 5, take away 2 to the power of 4 on your calculator, and that should give you the answer, which is 16. And we can write that up at the top as well. On our next question, we are integrating. Find the area under the curve between 2 and 3. And we have 4e to 4x. So you think about how the key works. When you integrate e, it's not going to change. We have e to the 4x. We've got that 4, I'm going to divide it by the coefficient on the x. And 4 divided by 4 is 1, so we've just got e to the 4x with the usual plus c. So now we can substitute into our equation. Start off with a 3. So e to the 4 times 3. We've got the plus c, which we know we don't need to write down. It's going to cancel out. Then we've got the 2. With e to the power of the 4 times 2. So then again, we could write out the numbers for e, and we're going to have to round it to a rational number. So it's going to be easier just to keep it as e. So we're going to have e to the power of 12, 4 times 3. Take away e to the power of 8, 4 times 2. And so we can write that directly into our calculator without any need to round. So E12 take away E8. My calculator got a little bit confused. You don't need a power symbol here. On my calculator, type E, and then type 12 straight after with no kind of power symbol. But make sure it works on your calculator. The answer you should get is 159,773.833 to 3 decimal places. And so E is a number that gets very, very large very, very quickly. The last medium example is another one with E in it. So take apart your integral notation, the numbers we're substituting, and just get down to the core of this, which is 15e to the 3x. So if we integrate that, we know that e is not going to change, but the 15 is going to be divided by the coefficient on the x. And 15 divided by 3 is 5. So we're going to have 5e to the 3x altogether plus c. So now we need to substitute. So 3 first. So we're going to have 5 lots of e to the power of 3x, which will be 3 times 3. Then we take away the smaller one, which is -2. So again, it's going to be 5e to the power of 3 multiplied by -2 this time. I've not written these because the c's are going to cancel out. So on my calculator, I'm going to want to write 5 multiplied by e to the power of 9, take away 5e to the power of -6. And if you type that into your calculator, you should get 40,515 and to 3 decimal places, 0.407. Always keep attention to how many decimal places you're being asked for. So I'm going to do 3 for all these questions, but you might be asked for significant figures or 1 decimal place or something else. For the hard questions, we're going to have a look at more interesting things that we can substitute into these equations. So again, all of these are going to have the integral notation, but we're going to have more interesting substitutions. This one, we've got pi by 3 and pi by 4. Now, the starting point is going to be to do the integration. And when we integrate sine, we get cos. So we get 6 cos x. Now, remember, a negative sign integrates to a positive cos. So a positive sign would integrate to a negative cos. So we have -6 cos x with our usual plus c. Now, the substitution part of this is where this gets interesting, and there's more than one way of doing it. Now, if you've got pi and you've got trigonometry, this means that it's talking about radians. So we're going to substitute in pi by 3 radians and pi by 4 radians. Now, if you're not comfortable with radians yet, one thing you can do is convert this into degrees. So radians are when a circle is measured in terms of 2 pi. Degrees is when a circle is measured in terms of 360. So if you want to go from radians to degrees to get from 2 to 360, you times by 180, and you want to lose the pi, so you divide by pi. If you want to go from degrees to radians, from 360 to 2, you're going to divide by 180, and then we want the pi in there as well, so we multiply by pi. So let's do this to pi by 3. If you do pi divided by 3, multiply it by 180, and then divide it by pi, you're going to get the number 60 for 60 degrees. If you do the same thing to pi divided by 4, or a quarter pi is another way of saying it, so multiply by 180, divide by pi, then you get 45 degrees. So let's go to the substitution. So we've got -6 cos of x, and so we can choose. We can either use radians or we can use degrees. So I'll do degrees for this question and radians for the next one, so you can see it both ways. So x would be 60 for 60 degrees, and then we don't need to write the plus c. We know that's going to cancel out. So next, substitute in the 45 degrees. That's going to be -6 cos of 45. So make sure your calculator is in degrees mode. There should be a D on the calculator screen somewhere. It should be in that by default, usually. So we do -6 multiplied by cos, open brackets, type in 60, and you should get a number. Now, I'm getting for this -3, which is quite convenient, quite a nice number. Then we can do -6 cos of 45. I'm pressing the back button on my calculator to change 60 into 45, and I get -4.24264 to 5 decimal places. Now that's a negative number, but we're taking away the second bracket, so that means it's going to end up being a positive version of that. So if you take that number and you take 3 away from it, then you should get a final answer of 1.243 to 3 decimal places. And again, we can write it up at the top as well. And again, that's going to be the area under the sine curve between 45 and 60. So now let's try that with radians. So firstly, we want to integrate. We've got -8 cos 8x. So cos x integrates to sine x. So we're going to have -8 sine of 8x. But when you integrate, you have to divide by the coefficient on the x. So that's going to give us 8 divided by 8 is 1. So that's -1 sine of 8x with the plus c. So now we're going to do the substitution. I'm going to do it with radians. So we're going to substitute pi in first. Now, before we do this, you need to change your calculator into radians mode, because if you substitute in pi as, pi is 3.14, for example, it's going to treat that as 3.14 degrees. Whereas in radians, it's actually representing 180 degrees. So you get a completely different answer. So there should be a mode button on your calculator. On mine, I press it twice, and there's a deg, rad, gra little notation. I press 1 for degrees, 2 for radians, and 3 for gradians. So I'm going to press 2 for radians, and now I can see there's a little on my calculator screen that tells me I'm in radians mode. So I can take my negative sine of 8x, but now x is going to be pi, and we can type that into the calculator. So again, negative sine, open my brackets, 8 multiplied by pi, close my brackets, I press equals, and I get an answer, I get 0. That's a nice, easy answer. So now I'm going to substitute in the other value, which was pi over 4. So if pi is 180 degrees, a quarter of that's going to be 45 degrees. Negative sine 8 multiplied by pi by 4, close the brackets, type it into your calculator, and I actually get 0 again. So we've got 0, take away 0 is equal to 0. So what does this mean? Well, it's nothing to do with it being a radians question. We'll do another radians question next. You can see a radians question actually giving you numbers. But what's happened here is that the kind of transformations of the cos curve. So the angle being multiplied by 8, the whole thing being multiplied by -8. What it's done is it's made it so that in between these values, there's actually no area. So the entire curve will be below the x-axis. So you might get a value of 0 sometimes. So let's look at a more typical radians question. So we've got 5 sec squared 5x. And we know that sec squared integrates to give us tan. So sec squared 5x will become tan of 5x. Now, the 5 that we had on the outside of the sec squared, that's going to be divided by the coefficient on the x. That's going to cancel out, leaving us with tan of 5x plus c. So now we're going to substitute in using radians and make sure our calculator still has that little highlighted on the screen. So we're in radians mode. So the largest one to substitute is not x by 5, it's x by 3. Because it's been divided by that number, so we need to divide it into less pieces to be larger. So we're going to have tan, and the angle is going to be 5 lots of pi by 3. Then we multiply together, and then we take away from that, we're going to substitute in pi by 5 next. That's going to be tan, and the angle is going to be 5 multiplied by pi by 5. So we can put this into our calculator. So press tan, open the brackets, 5 multiplied by pi, divided by 2, close the brackets, and we get negative 1.73205 to 5 decimal places. Then I'm going to press the back button on my calculator, change divide by 3 to divide by 5, and for that one we get 0. So this is quite common in trigonometry. So we know our answer, we're taking away 0, so I'm going to say the same. It's going to be negative 1.732 to 3 decimal places. Now the next question is even more interesting because we just strip away the integral notation. We're substituting in e to the power of 0 and e to the power of 2. This is much more complicated in what we're substituting. Now again, our first step is going to be to integrate. So when we integrate this, we're going to get ln x over 8 plus c. So we can write out our substitution. So we're substituting e to the power of 2 into ln, swap the x for e to the 2, and then that's going to be to the power of 8. Close the brackets, and we're going to take away the same thing for e to the power of 0. So ln x, the x is going to become e to the power of 0, and that's going to raise to the power of 8. Now, there's a few ways to tackle this. So, for example, you could take step by step, we'll start inside the inner brackets and go, well, e to the power of 2, and get that answer in your calculator. It's about 7.4. Then you can raise that to the power of 8, which will give you, looks like it's just under 9 million. And then you can take the ln of that number, and it's going to give you the answer, which is 16. That would be quite surprising. It's quite a simple number to get out of when we're just below 9 million with lots of decimal places. So what's going on? Well, we can use the laws of indices. So we can say that this is going to be the same as ln, and then e to the 2 to the 8, use the multiplication rule, 2 times 8 is 16. It's going to be ln e to the 16. So that's the first thing we're going to look at. Then you realize, well, we've got a 16 there, our answer's 16. And you've got to know that ln and e are actually opposites of each other. They're inverse operations. So that means they're going to cancel out. So we get 16. So we can do the same thing on the other side. We can say, well, we're going to have ln as e0 times 8. 0 times 8 is 0. It's going to be e to the power of 0. And ln and e cancel out. So it's going to be 16. Take away 0. And the answer is 16, which we can write in. So again, two methods. Use your calculator. Do it step by step. If you try and put it on all at once, your calculator might get confused. So do the e part, then do the power, then do the ln, 3 steps, and you will get your answer. But it might be a little bit faster if you can kind of use solving equation skills, laws of indices, and work it out that way. So now moving on to our final question. And again, stripping out the integral notation and looking at what we're substituting. We're going to be substituting e values in again, but we're going to start off by integrating what's left, which is the negative 2 over x. And that's going to give us a negative ln x squared plus c. So write out your substitution. It's really important that you do this as well because the examiner can see what you're trying to do. So you make a mistake, but you rotate all the notation, then you're still going to get a bunch of marks. X is going to become e to the power of 5, and that's going to be raised to the power of 2. We can know the c's, we know they're going to cancel out. On the other side, we have negative ln. E is going to be e to the power of 3, and that's going to be raised to the power of 2 as well. So again, you can put that into your calculator, but it's going to be easier to use the laws of indices here. So we're going to have the negative ln e to the 10, 5 times 2 is 10. And we're going to take away from that, we're going to have a take away a negative, that'll give us a positive. That'll be ln e to the 3 times 2 is e to the 6. Then we know that the ln bits are going to cancel out. So the ln and e cancels out, leaving us with just 10. And on the other one as well, leaving us with 6. So we get negative 10 plus 6, which altogether is negative 4. So we can write negative 4 down as our final answer. And you'll find what's happening here is a common thing where you get some ridiculously complicated numbers and notation, but then actually they simplify something quite nice and easy at the end.